the title of the conference is Glimpses of the Invisible. And I would like to suggest that in my talk, there will be actually a move from the visible to the invisible. So let's see how it works. It is hard, let's move, that will be the structure. It is hard for us to imagine that before Kepler, astronomers didn't track the path of a planet. Rather, the practice was to develop methods for finding the positions of a planet at any given time. This is what is called positional astronomy. Up to Kepler, astronomers didn't graph these positions even when they constructed an ephemeral, a list of planetary positions at intervals of a day or a few days. In other words, in this traditional astronomy, positions at a planet was not associated with a path. Moreover, astronomers in this long-standing tradition only considered two dimensions, celestial longitude and latitude, effectively projecting the planet's position onto a unit sphere with the Earth as center. The third dimension, distance from the center of motion or depth, be it the Sun or the Earth, was considered in a different domain, namely cosmology, where the geometric models were transformed into a system of orbs, solid spherical shells to which the planets were attached. So, so here we have the orbs, 1535, and the planets are attached to the orbs. But unlike celestial longitude and latitude, planetary distances at a given time were not computed. We ask, what led to the change by which astronomy and cosmology were set on a new foundation where a planet was associated with a trajectory? We show that by introducing the concept of path into astronomy in response to a new problem, Kepler undermined traditional astronomical and cosmological theories and single-handedly revolutionized the practice of astronomy. Kepler and astronomers after him have been engaged in determining the path of a planet and the physical laws governing its motion, and this is the critical background to the Newtonian development of celestial mechanics. To understand Kepler's achievement, we begin by examining a few critical features of the practice of astronomy and cosmology in the 16th century, shortly before Kepler entered the scene. We then analyze the way a concept may fundamentally change a long-standing practice, thereby throwing light on the dynamics of scientific change. So first, the distinction between astronomy and cosmology. Astronomy and cosmology were conceptually distinct. In astronomy, geometric models, think of them as hypotheses as they were traditionally called, were constructed from which the position of a planet could be computed either directly or by means of a set of tables. In cosmology, one had to fix center of motion, the Earth or the Sun, and then establish the arrangement of the planetary orbs in space where it was assumed that the motion of the planet was due to motion of the orb to which it was attached. Many astronomers in the 16th century still adhere to Ptolemy's cosmology, in which the planetary orbs were centered on Earth with no space between successive orbs based on geometric models. For Copernicus and his few followers in the 16th century, the center of motion was the Sun, and the planets were still attached to orbs. I think this is very critical to keep in mind that for Copernicus, there are still orbs to which the planets are being attached. So the cosmologies with the Earth as center of motion and that with the Sun as center of motion were very different. But what about the underlying geometrical theories, the astronomical theories? Were they also different as the cosmologies? Again, the cosmology is completely different in Copernicus if you compare it to the previous traditional astronomy. So the cosmology is different, but the astronomy, and the question is whether the astronomy is different. Surprisingly, the answer is no. Adherence to what is now called the Wittenberg interpretation of Copernicus accepted Copernicus' innovation in astronomy without any commitment to his cosmology, for Copernicus tables and derivation from them could be used to find the position of a planet as seen from Earth with very much the same rules as had been employed previously in the Ptolemaic tradition. In other words, for these astronomers, notably Reinhold, for example, Copernicus' astronomy was independent of his cosmology. Indeed, most of Copernicus' magnum opus, De Revolutionibus, is devoted to astronomy. So De Revolutionibus is very much in the tradition, in the old tradition, where you separate the cosmology. It's not that you separate, you conceived of it separately, the cosmology from the astronomy. I move to the second claim. Copernicus lived most of his adult life in Fromburg, Poland, without regular contact with other astronomers. He was unable to oversee the production of his book, De Revolutionibus, and this task fell to Andreas Osiander, a Lutheran theologian, and Osiander added an anonymous preface to Copernicus' work. The view expressed by Osiander were widely accepted at the time, particularly by philosophers, although not by astronomers to the same extent. So he wrote in the, no, it doesn't work. Oh, here it is. So here is what Osiander has in the preface to the Revolutionibus. It is the duty of an astronomer to devise the causes of these celestial motions or hypotheses about them. Since he cannot in any way attain to the truth of the causes, he will adopt whatever suppositions enable the motion to be computed correctly from the principle of geometry for the future as well as for the past. Note that the prediction and the retrodiction is the same practice in terms of the computation. The present author, namely Copernicus, has performed both these duties excellently. For these hypotheses need not be true, not even probable. Since different hypotheses are sometimes offered for one and the same motion, for example, eccentricity and an epicycle for the sun's motion, the astronomers will take as his first choice the hypothesis which is the easiest to grasp. The philosopher will perhaps rather seek the semblance of truth, but neither of them will understand or state anything certain unless it has been divinely revealed to them. There are 2 points to emphasize in this preface. 1, there is no claim that the cosmological system proposed by Copernicus concerned the sun is real. And 2, that one cannot decide which hypothesis represents reality when 2 of them are geometrically equivalent, as is the case with the eccentric and the epicycle. So these are the 2 options, either an eccentric or an epicycle. You can see that there are 2 options here for representing the motions of the stars, the planets. In other words, Copernicus offered an alternative to Ptolemy. Indeed, he offered an alternative, but he had no physical proof that heliocentrism is true. Osiander's famous preface has been taken to be an example par excellence of instrumentalism, namely that a physical theory is just as a means of calculation which may have no relation to reality. However, although Copernicus did not address this metaphysical issue directly, namely how real his theories were meant to be, there is no doubt that his book, that he took his cosmology to describe reality. The key observational discovery that changed cosmology was Tycho Brahe's demonstration that the comet in 1577 was above the moon. Previously, comets had been assumed to be sublunary phenomena. it followed that Aristotle's distinction between the physics of the sublunary world and the physics of the heaven was not valid. Moreover, by tracking the comet's path in space, it was clear that there are no solid orbs in the heavens. The comet simply moved unhindered by solid orbs. Surprisingly, the community of astronomers did not take the dissolution of the celestial orbs to be a crisis. But it raised the following question. In the absence of orbs, what keeps the planets in space and what causes them to move? Again, to a modern reader, this appears obvious and even trivial. But at the time of Kepler, no one realized that this was a fundamental problem in astronomy. Ultimately, Kepler provided the answer in his Astronomia Nova. So the title is very revealing. New astronomy based on causes, celestial physics treated by means of commentaries on the motion of the star Mars from the observations of Tycho Brahe. So this is very revealing because you get in a nutshell in this title all the elements that actually make the revolution in astronomy. And you can see it has to do with physics, it has to do with causes, and it has to do with observation and combining together in a coherent fashion. We restrict our attention to the first two chapters where Kepler undermines some aspects of traditional astronomy before presenting his new astronomy, which was in fact revolutionary. The fundamental idea is that in the absence of orbs, the path of the planet has to be explained causally, as stated in the title of the book, Celestial Physics Based on Causes. It is evident that the search for a celestial physics based on causes to account for the path of a planet calls for a fundamentally different scientific practice from that of positional astronomy. Moreover, the distinction between cosmology, concerned with the real distances or depths from the center of motion, and astronomy, concerned with celestial longitude and latitude, is no longer relevant because the path of the planet takes the places in 3 dimensions: depth, longitude, and latitude. So by actually constructing astronomy on the basis of these principles, cosmology and astronomy becomes one. They are not anymore separated. So Kepler begins in the first chapter with a statement of the problem. Circles are considered the most perfect. However, when experience is seen to teach something different, of course, he was arguing for a different path, namely that the planets deviate from a simple circular path, it gives rise to a powerful sense of wonder, which at length drives men to look for causes. Kepler implied that the community was aware of the problem he raised, but this was certainly not the case. Here we have the first of Kepler's many rhetorical moves. So obviously he was much concerned with this problem, but the community was not really aware of this difficulty. Kepler described retrograde motion in terms of the planet's distance from the Earth. This was not the traditional way of describing it, where the successive position in longitude were noted rather than the distances from the Earth or the variations of apparent size. So he then presented a figure for the path of Mars around the Earth from 1850 to 1596 in longitude and distance from the Earth. A complex set of loops, which he called a pretzel or a spiral, that had never been seen before. In fact, the concept of path allowed Kepler to draw this figure without changing the underlying astronomy. Anyone before Kepler could have drawn this figure, but no one did. because the absence of the concept of a path in astronomy. So although the planet's motion had been considered to be the sum of uniform circle of motion with respect to Earth, the resultant path turned out to be a much more complicated figure. He then compared this pretzel to the simpler path of a planet around the sun. So you see the pretzel, how complicated it looks if the center of motion is actually the Earth with respect to Mars. Then we can move to this. So, sorry, no, let's save this. So the goal of chapter 1 was to undermine, or we can actually, so the goal of chapter 1 is to undermine the confidence in traditional geocentric and astronomical theories. By appealing to the concept of paths, Kepler argued that such theories implies the path, the pretzel, that is extremely intricate. By contrast, a heliocentric astronomical theory entails a simpler path, which is very nearly circular. It is likely that Kepler intended to undermine the Wittenberg interpretation of Copernicus, according to which it was a matter of indifference whether one interpreted Copernicus' astronomy as geocentric or heliocentric, because in either cases the position of the planets as seen from the Earth are the same. Here, Kepler demonstrated that although the position in celestial longitude and latitude are the same, the paths are different. Moving on to chapter 2 of the Astronomia Nova, the geometric equivalence of the eccentric and the epicyclic models were proved in Ptolemy's Almagest and was frequently cited in the subsequent astronomical literature. The issue in the 16th century was not, however, the geometric equivalence, but the assertions of the absence of physical equivalence. That is, there was no way to decide issues except by traveling up to heavens and checking and seeing which is the right arrangement. And Kepler's insistence on physical causes was new and in fact resolved the issue. At this point of the argument, Kepler introduced the standard concept of orb and discussed the well-known views of Aristotle and his followers. In proposing these Aristotelian orbs as objects of contemplation, two things will present themselves to us: the motive force, sufficient for the round orb, from whose activity and constant strength the time of revolution arises, and second, the direction in which it acts. The former is more correctly ascribed to the animate faculty, and the latter to its intelligent remembering nature. Now, it is quite true that through this solidity of orbs, all motions of celestial appearances are so provided, for that nothing is left to the providence of the presiding movers. Indeed, the whole variety of motion is a consequence of the number of dispositions of the orbs. Kepler continued by presenting an analysis based on inherent forces, which he then refuted. He summarized his argument as follows: anyone who says that the body of a planet is moved by inherent force is just plain wrong. A perfect eccentric circle drags many incredible things into physical theories because it ascribes incredible faculties to the mover. The key point is that prior to Kepler, it was agreed that one set of orbs or another was in the heavens. The problem was the impossibility of deciding which one was really there. That is, the orbs were neither fictional nor astronomical. Kepler opposed this view, also expressed, as we noted, by Osiander in his preface to the Revolutionibus. Kepler argued that since the orbs had been eliminated by Brahe, the problem disappears. One no longer needed to choose among competing sets of orbs. This meant that the physical interpretation of the eccentric and epicyclic models in terms of orbs was no longer valid. In a conversation between Vamos and Tycho Brahe, Ramos advocated an astronomy without hypotheses, namely models. Brahe replied that astronomy without hypotheses was impossible. The apparent motions of the planets could only be represented by circles and other figures. Brahe's view was standard. The role of an astronomer was to produce geometric models to account for observed position of the planets in longitude and latitude. So this is very visible. I mean, you can actually present it as we've seen with the orbs. By contrast, in response to Ramos' challenge to astronomers published in 1569, Kepler claimed to have produced an astronomy without hypotheses that would have satisfied Ramos, were he still alive. For Kepler, new astronomy was based on physical laws accounted for the path of a planet in 3 dimensions. Practitioners of the new astronomy developed celestial physics, no longer constructing geometrical models to account for the position of the planet. So, to conclude, the problem of the sets of orbs, one for the eccentric model and another for the epicyclic model, I recall again these 2 options of either the eccentric, this is the E, the OD, then the E, or the epicyclic on the circle itself. So the problem of the 2 sets of orbs, one for eccentric model and one for the epicyclic model, was well known. Kepler, in effect, came up with a solution to an old problem in cosmology, namely that despite the geometrical equivalence of these 2 models, the corresponding sets of orbs were not equivalent physically, and it was not possible to know which set of orbs was in the heavens. In the absence of orbs, Kepler proposed that astronomers and cosmologists focus their attention on the path of a planet and then seek physical causes for this path. Astronomical theories in the form of geometrical models lacked a causal argument, and without orbs, cosmology lacked causal argument as well. The concept of path led Kepler to seek causal argument. What force moves the planet to take the path it takes? This approach transformed both astronomy and cosmology. And finally, Kepler's eliminated the distinction between astronomy and cosmology, for the path of a planet in space involves all 3 dimensions quantitatively. Thus, the concept of path transformed the practice of astronomy and cosmology and led to a new astronomical theory. As a consequence of discarding one concept, namely orb, and replacing it with another, namely path, we witness a change in the way a practitioner approaches the subject. The revolution is an underlying conceptual foundation which subsequently requires a change in theory. It is perhaps not surprising that the change takes place in the first instance in practice, not in theory. So, although Copernicus introduced a new theory in terms of his practice, he belongs to the long-standing tradition that goes back to Ptolemy. Copernicus made use of the same tools that his predecessor used. As noted above, his tables for planetary motions were very similar to those of his predecessor, both in structures and in theory, in their entries. With Kepler, the task of astronomers, namely the practice of astronomy, was no longer to find a geometrical model to account for a planetary position. Rather, the task now was to find physical causes to account for the path. The practice had to change, and subsequently the theory. What has been called the Copernican revolution should be changed to Keplerian revolution. The revolution was essentially the introduction of a new concept, path, and determination of its physical causes. Thank you.